Okay, so measures of position, mostly it's going to be our box and whisker plots that we're talking about in this section. You guys have done this before, so we're going to kind of jump through some of this basic stuff to start. So when you make a box and whisker plot, we create what's called a 5-number summary. Some of this we've done already. So we have a minimum, which is our lowest value, a maximum, our highest value, median right in the middle, and then we create a lower quartile, which we refer to as Q1, and an upper quartile, which we refer to as quartile 3. It basically takes our data and it splits into 4 even groups. So we're finding a median 3 times. We find a median of our full data set, that splits it in half. And then the upper quartile is the median of the top half of the data, and the lower quartile is the median of the bottom half of the data. And then those 5 numbers create our 5-number summary. All 5 of those you can see in your graphing calculator. When you do that 1 variable or 2 variable statistics, it's part of that big list that the calculator gives it to you, and it gives it all in order. It says min, Q1, median, Q3, max. Okay. So one thing that sometimes gets tricky when we do these, it's always a question, is about whether we have an odd number or an even number set of data, how it splits our data in half when we have to split it in half and then split it in half again. If you have an odd number of data values, we know that the median is going to be a single number in the middle, okay? So we don't have to worry about like averaging 2 numbers together. Then to find the upper and lower quartile, you do not include that middle value. So we've already used that, and you can see there's a set of like 9 numbers here. If I were going to find the lower quartile, I would just find the middle of those 4 values below my median. And if I were going to find the upper quartile, I would find the middle of the values at the top there. So here my Q1 would be 4, and my Q3 would be the middle of those, so 9.5. Okay, so we are not using the median in that upper and lower half when we find those. If you have an even number of data values, we find the 2 in the middle, and we find the median from there. So that's actually at the bottom of the screen there. You can see the middle of 7 and 8 is 7.5. And again, the median that we have is not used when we find the lower and upper quartile. So we don't use that 7.5, but really all of the other data values that were in the original set are still being used here. Just the median value is not being used. So I have 5 values below here. So the middle of those would be 5. That would be my Q1. I have 5 values on the top. The middle of those would be 11. That's my Q3. And of course, it hopefully goes without saying that your numbers have to be in order when you're doing this, least to greatest before anything happens. Okay, so is this problem on your paper? I think yes. Okay. All right, so let's do it. Find the quartiles of a data set. So each year in the U.S., automobile commuters waste fuel due to traffic congestion. The amounts in gallons per year of fuel wasted by commuters in the 14 largest U.S. urban areas are listed, and they're conveniently in order for us already. Tomorrow we're going to do an activity in Google Sheets, spreadsheet, where you can very quickly order data. So right now we're not going to spend a ton of time doing that. And we've got 14 of them, so that's helpful to know too. We've got an even number, okay? We want to find the first, second, and third quartiles. The second quartile is the median. Sometimes they'll say Q2 or sometimes they'll say median. It means the same thing. So we're going to find our median first. If I have 14 data values, which numbered data values are in the middle? You can count your way out, or you can just count up to what number? What's half of 14? 7. 7 and 8 are going to be in the middle. 1, 2, 3, 4, 5, 6. There's 7. There's 8. You can confirm that there's 6 numbers on either side of those. And I would find the middle of those, which would be my median or my Q2, which is what? 25. Okay, now that median is in between 2 of our data values. We're not using the median, but we're using everything else. So those 25s are being used now to find the upper and lower quartile. In the upper half and the lower half, I have 7 data values. I want to find the middle of those. So what number do I need to count up to? 4. The fourth one in either direction is going to be my Q1, in my Q3. It's right in the middle, no need to average. There are my quartiles, and if we want to finish our 5-number summary, it's easy then to name the min and the max as well. Okay, questions there? Great, moving on. Okay, using technology, I think we're going to skip this one. Are we all good with the one variable statistics? It's just that same thing again. Okay, so you can put it in your stat, list one, and then just calculate one variable statistics if you want to make a note to self. One variable stats under calc is how we do that. We've already practiced it a couple times, so you guys should be good with that. Tomorrow with the spreadsheets, we'll find another way with technology to do this as well. Okay. Making a box and whisker plot now. So you found your 5-number summary, you divided your data into your quartiles, into fourths, and you have those data values listed here. How we make a box plot is it's going to start kind of like our dot plots. So we're going to have a number line at the bottom. If we knew what this data represented, we'd want to label that number line with something. We don't know what it represents, so we're just going to kind of leave that alone right now. When you make it, a box plot either goes above or below the number line. Doesn't really matter which way. Usually it's above, but if you want to do below the number line too, that's fine. All right, we're going to make dots above at each of those 5 values, okay? So 5, 9, 13 and a half-ish, 23, and 32. Once you have your 5 dots, the 2 pairs that are on the extreme ends are going to form whiskers. Sometimes it'll stay like this. Sometimes you might even see like a little, I don't know, kind of like tag on the end of them. That's optional. The 3 dots in the middle then form the box. And the median will create a line somewhere in the box. It's important to remember that we are dividing our data into fourths. So no matter how big each section here is, each part of the box and whisker graph represents 25% of the data. So when you see a very small part of a box and whisker graph, maybe like on the left side here, this whisker or this part of the box, it means our data is very condensed. We have a lot of data values in one spot. And when we have a longer part of a box and whisker graph, it means your data is more spread out in those areas. It's still 25% of the data, but you've just got a larger spread in the data in those regions. Okay. All right, interquartile range is something that we can do a quick calculation with. You can write this formula down somewhere. It is just the difference in your upper and lower quartiles. Q3 minus Q1, we use IQR to represent it. Okay, and then you guys have this on your paper. Why don't you, with a partner, go ahead and see if you can use what we've talked about so far to answer these 4 questions. With the partner group, give you a few minutes. These are approximated because we're trying to read off the number line there. So if you're within like 1 or 2 units of those answers, it's not necessarily a bad thing. The median is that line right in the middle of the box, 30. The range is your max and your min, highest minus lowest. We've practiced that a few times this chapter, so it's about 42. Interquartile range is just Q3 minus Q1. So just the edges of your box are represented on those. So about 15. And then between 14 and 38, you've got 3 sections of your graph. Each section is 25%, 75% total. Okay? Questions on this? All right, moving on. Okay, so what do we use interquartile range for? Interquartile range helps us figure out mathematically if we have an outlier. Up until now, we've just kind of looked at data and said, oh, we kind of think it has an outlier. It looks like that number is like really big or really small. We're not sure. So here's how we're going to calculate it, and we're going to do it on the next example in a second here. So you're going to find your Q3 and your Q1. You can even find the 5-number summary a lot of times to start. Then you're going to take your interquartile range and you're going to multiply it by 1.5. And sometimes, if you've ever done this before, the teachers will call that like the magic number. Okay. To find the lower bound and an upper bound that are going to be the boundaries for our outliers, meaning if there's a number above that boundary or a number below that boundary, it's an outlier. To find the bounds, we take our lower quartile Q1 and subtract that number. So we're subtracting 1.5 times the interquartile range. And we take our Q3 and add on that magic number, so 1.5 times the interquartile range. If any data values are beyond that, they're outliers. If all of our data are within the bounds that we found, we don't have any outliers. Okay, so we're going to do an example so you can see what this looks like. This one, I think, is on your paper. All right, so we're going to find the quartiles, interquartile range, and then use the interquartile range to see if we have outliers. So let's start with dividing it in half. How many numbers do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 16. So I've got to split it 8 and 8. 1, 2, 3, 4, 5, 6, 7, 8. Right in the middle. So my median, my Q2, is going to be 60. Right in the middle of the 60s. Okay, then we take the top 8 and the bottom 8 and divide them in half again, because those are even numbers. We're going to pick 2 that are in the middle and then find the average of them, like we just did a second ago. So the 2 in the middle and the bottom are 57 and 59. The middle of those will be my first quartile, 58. The middle of the top are 63 and 63. The middle of those is also 63. And then again, if you want to complete the 5-number summary, once they're ordered, it's easy to see min and max. Okay. All right. To find the outliers, we first do our interquartile range, which is Q3 minus Q1, 63 minus 58 is 5. Okay. Then we do our interquartile range always times 1.5. So in this problem, that's 5 times 1.5, which is 7.5. Then Q1 and subtract that number, Q3, and add that number. So our Q1 was 58, subtract 7.5. Our Q3, 63, add 7.5. All right, so let's see. 58 minus 7.5 is 50.5. That's a lower bound. 63 plus 7.5 is 70.5. And that is an upper bound. These are boundaries that your data should lie between. Are there any data values in the set that are beyond those boundaries? Yes? 80? So we can say, therefore, 80 is an outlier. You can have more than one outlier. If there's more than one data value that lies outside the boundaries, they're all outliers, however many there are. Okay, so we mathematically prove that we have an outlier. It's a hunch if we look at it, but you can prove it this way. Questions there? Finding an outlier. Great, moving on. Okay, percentiles. So quartiles divide things into 4. We have deciles that divide things into 10. We don't use those as much. Percentiles we use a lot. Percentiles divide things into 100. Cent, it's got that part of it, right? Does that mean 100? So when we have percentiles all the way from 0 to 99. I don't list 0 there for some reason, but 0 to 99. When you are in a percentile, it means that percent of the data is below you. So you can't be in the 100th percentile because it would mean 100% of the data lies below you, and that's everybody, including you. You can be in the 99th percentile, though. 99th percentile means you're number 100, and 99% of the people are below you. Okay, you can be in a 0 percentile. When my son was born, he was 4 pounds, 4 ounces. He was in the 0 percentile when he was born. He wasn't even on the chart because he was so tiny. Because out of 100 babies born, he was number 0, right? Or number 1, I guess. So that's what percentiles mean. It's a percent of the data that lies below what you're calculating, okay? And here's how we're going to calculate it, and we're going to do it in a second. Find a data set. Let's say I want to know number 10 is in what percentile of this data set. The first thing I do is count the number of data values that are below that number 10, which here it's 16. They've done that for us already. You divide it by how many data values are total. In this example, there's 20. 16 over 20, if you do that math, is 0.8. Turn it into a percentage, 80%. So that means 10 is in the 80th percentile, which tells us 80% of the data lies below 10. The question that usually follows that is what percent of the data lies above 10? Well, if 80% lies below, that means I'm number 81, right? Imagine like 100 people in a line. If 80 are below me, I'm number 81. So how many people are above me? If there are 100 people in line. What do you think? There are 19, okay? So if 80% are below, 19 are above. Make sense? Okay. All right. So let's do an example. Is this one on your paper? No? Okay, this one's more like just reading a graph, honestly. It says the OGIV graph represents cumulative frequency for SAT scores of college-bound students in a recent year. What score represents the 80th percentile? So percentiles are over here, and they've kind of drawn the line in for you already. If I want to know what score correlates, you can just find the percentile, go over to the graph, and then go down to find the score that's associated with it. So here, I would say it's like 1250. If I wanted to find the score that's associated with the, I don't know, 40th percentile, I would go over until I hit my graph, go down, maybe somewhere between 1,000 and 1,100, okay, depending on, you know, how accurate I wanted to get with that. So that's more just reading a graph if you see percentiles. Calculating a percentiles, I think you guys have this one now, okay? We want to know what percentile rank is a score of 60 in the data set below. And again, it's already ordered for us. So 60 is the guy we're trying to calculate. What percent is below? We're going to calculate how many numbers are below. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 13 data values below 60. Divided by how many data values there are total. Looks like there's 23. Divide it, get a decimal, turn it into a percent. 13 over 23 gives me about, if I round to the nearest couple decimal places there, 0.57, about 57%. So what percent of the data is going to be above? If we're in the 57th percentile, what percent of the data is above 60? 43%. Close. 42%. Just take one away from that, okay? Because if 57% is below me, there is one additional guy, me, and then I have to count everybody above me, okay? All right, last thing that is in this lesson is z-score. Z-score is going to be a really big idea really soon, like chapter 5, 6, 7, 8. You guys won't be able to get through a problem without talking about a z-score. So it's a really big idea. Is this on your paper? If it's not, write it down. All right, so a z-score tells us, now we're back to yesterday, how many standard deviations we are away from our mean, okay? And usually the number is going to be between -3 and 3. Remember we talked about that yesterday, 3 and -3 were like the far ends of our bell curve, that many standard deviations. So if I have a z-score of 1.2, it means I'm 1.2 standard deviations to the right of the mean. Or if I have a z-score of -2, it means I'm 2 standard deviations to the left of the mean. So the positives and the negatives are important. If it's a positive z-score, you're to the right of the mean. If it's a negative z-score, you're going to be to the left of the mean. And all we are doing right now is figuring out what is our z-score. We're going to interpret these and stuff later in future chapters. How we calculate it is you take your data value x, whatever it is, you subtract your mean, and you divide by the standard deviation. Now, those are all the population symbols. You will also see it written this way. Remember, the other way we can see mean written is x bar if it's a sample, and it might be an S if it's a sample for standard deviation. They mean the exact same thing. Okay, so finding a z-score. The mean speed of vehicles along a stretch of highway is 56 miles per hour with a standard deviation of 4 miles per hour. You measure speeds of 3 cars traveling along this stretch of highway as 62, 47, and 56 miles per hour. Find the z-score that corresponds to each speed. Assume the distribution of the speeds is approximately bell-shaped, and you guys have the sample formula there. All right, so we're going to do this 3 times for 62, for 47, and for 56. For each of these z values, we're going to take the x value that we have, so 62 for the first one, minus our mean, and they've saved us some time. They told us what that was. It was 56, divided by our standard deviation, 4. That will give me 6 over 4, 1.5. If you have to round, we're going to round z-scores to 3 decimal places. Okay, so that's my z-score, 1.5. That's it. Very quick calculation. Same thing with 47 now. The only thing that's changing is your x. 47 minus our mean divided by 4. So that gives me -9 over 4, -2.25. 56. So hopefully you get something ringing in your head saying, wait, that's the mean. So if I'm at the mean, how many standard deviations am I away from the mean? I should expect to get a 0. So if I were going to look at a picture of what we just did, think about that bell curve from yesterday. We have a mean of 56. We could even label all the standard deviations if we want to. Right? We can go up by 4 and down by 4 like we did yesterday. You can find 62 is going to be over here. It's telling us that it's 1.2 standard deviations to the right, or 1.5 standard deviations to the right. I guess I should make that a little bit further out. Okay. 47, -2.25. So 47 is going to be down there somewhere in my data set. And then 56, of course, is already labeled. We've got that one on there. Okay, so it's just locating something on that bell curve for us, which is going to be important later. So we're going to figure out percentages, and it's going to help us with probabilities. There's going to be a lot of applications after we're able to locate something on this bell curve, a specific data value for each x. Okay. All right, this is the last problem for the day. So it says comparing z-scores from different sets. I'm going to let you guys try this one. I want you to compare the z-scores for a 6-foot-tall male versus a 6-foot-tall female. And that's feet. You've got data values in inches here, so you're going to have to do a quick little conversion. Okay, so find 2 z-scores for me. One for the males, one for the females. Should be a quick little calculation. Oop. There are your answers. So the male z-score is a 0.7, which is within 1 standard deviation. So that's pretty normal for a male to be 6 feet tall. When we calculate it for a woman, though, we end up with a z-score of 2.96, which is pretty high. So we're almost 3 standard deviations out. Remember I mentioned yesterday, if you are more than 2 standard deviations in either direction from your mean, then it is considered an unusual data value. So that is unusual, we would label it. Okay, so that'll just be a quick question usually on Math Excel. Usual or unusual, we just say unusual. All right, and that's it. That's everything from chapter 2, complete, finished. All right. So you guys have circuit training bonus if you want to work on it. You've got Math Excel. You've got 2-4 Math Excel, which is due on Friday. Is that right? And then 2-5 is due on Monday. So 1 due on Friday, 1 due on Monday. Those are the last 2 Math Excels for about a week. And then tomorrow we're going to get some M&Ms out. We're going to do a little spreadsheet activity. So make sure you have your Chromebook ready to go because you're going to need to get into Google Classroom stuff for all that. All right, we'll do cell phone lotto, and you got about 10 minutes left to work on homework.